Flexural behavior of lightweight polymer concrete slab reinforced with glass fiber reinforced polymer bars. Abstract: the flexural behavior of polymer impregnated lightweight concrete reinforced with fiberglass-reinforced polymer, GFRP, bars was examined in this research. The primary distinction between lightweight and regular concrete is the reduced density mass. Using lightweight concrete minimizes the structure's dead load, allowing the structural designer to shrink the size of the column, footing, and other load-bearing elements. Because lightweight concrete is non-structural, polyester is employed in structural engineering to create a new generation of lightweight concrete impregnated with polymer. In addition, to resist flexural and tensile stress, glass fiber reinforced polymer, GFRP, is used in slabs. Keywords: recycling, external strengthening, GFRP, green concrete, lightweight concrete, fibrous concrete. 1. Introduction. For many decades, lightweight concrete is considered non-structural concrete because the aggregate utilized is of a special nature. Compared to conventional weight concrete, which has a density of 2,240 to 2,400 kilograms per cubic meter, structural lightweight aggregate concrete, SLWAC, has an in-place unit weight of 1,440 to 1,840 kilograms per cubic meter. The cylinder compressive strength should be greater than 17.0 MPa for structural applications. In most cases, the marginally higher cost of the SLWAC is offset by size reduction of structural elements, less reinforcing steel, and reduction in concrete volume, resulting in lower overall cost. 1.7. Lightweight aggregate plays the primary role in reducing the density of concrete, which helps to reduce the own weight of the slab and reduce the dead load in general on the structure, especially on the building foundations. The use of lightweight porous concrete is a new approach to obtaining small concrete density, but this is at the expense of concrete strength. Polymers are the best solution to overcome the weakness of concrete strengths. Hence, they can combine the concrete components, which helps integrate the molecules to improve concrete behavior. 8.9. Despite the additional cost of utilizing polymers and their significant weakness in resisting fire and heat, it is considered the best choice for submarine buildings that are exposed to steel rust. To complement the innovative idea in this research, glass fiber reinforced polymer, GFRP, bars have been utilized as the main reinforcement for studied slabs. Utilizing these bars enhances the bond between these bars and the polymer material because these bars are made of the same material, which improves the behavior of the composite material significantly. 10.16. This research contributes significantly to the use of modern and innovative materials to obtain low-density concrete while maintaining the mechanical characteristics as well as improve flexural strength if it is utilized in concrete slabs and overcome the problems of rust of main steel reinforcement. By combining some of the previous studies, we can summarize them as follows. Fiber-reinforced polymer composites, FRPCs, have developed as a relatively new construction material capable of addressing many of the shortcomings of existing construction materials. 17. Glass fiber reinforced polymer, GFRP, bars are a non-corrosive alternative reinforcing solution for concrete constructions that are less expensive to maintain and repair. 18. This non-magnetic alternative reinforcement is lighter than steel and has a higher tensile strength. 19. 20. GFRP bars have been effectively utilized as internal reinforcement for concrete structures in many studies, including beams 21, columns 22, and slabs 23. Because slabs are the main structural parts in a structure, they consume the most concrete and contribute significantly to the dead load. 24. They should be constructed to use the least amount of resources and to be as light as possible. Previous studies 25, 26, drilled holes in the slab to lower the amount of concrete utilized and the overall weight. Polymers improve the mechanical and chemical characteristics of concrete, including increased compressive strength, flexural and tensile strength, good performance and durability, and reduced corrosion and permeability. Polymer impregnated concrete, PIC, polymer concrete, PC, and polymer-modified concrete are the three types of concrete that contain polymer, PMC. Polymer concrete has higher compressive, tensile, and flexural strengths, durability, low permeability, reduced corrosion, excellent adhesion to concrete and steel, and resistance to freezing, thawing, and acid attacks. However, the disadvantages include higher costs, more complex runs, and contractor unfamiliarity. Polymer concrete is appropriate for marine works, nuclear power plants, sewage works, desalination plants, corrosion-prone pipes and pumps, tunnel lining, and storage water tanks. Victor Yehia et al., 2003, Polymer concrete, PC, composites have a different set of characteristics that vary depending on the formulation. The variations in polyester polymer concrete mixture components that affected the characteristics were examined in this study. The impact of resin content, aggregates, fibers, and coupling agents was scrutinized. It was discovered that the optimum polymer content ranged from 12% to 14%, W/W. Utilizing fibers and coupling agents improved the mechanical characteristics of PC even more. In addition, a new database was created to document various PC characteristics. 27. John Kongshen et al., 2004, the influence of polymer addition on the microstructure, performance, and mechanical characteristics of lightweight aggregate concrete was looked at. The addition of polymer to lightweight aggregate concrete increased its performance and mechanical qualities. The improvement of mechanical characteristics was determined to be due to the alteration of microstructural homogeneity and densification with the addition of polymer. The lightweight aggregate concrete with 13% ethylene acetate ethylene interpolymer, EVA, demonstrates favorable mechanical qualities in compressive strength and bending strength. 28. Gouda et al., 2009, discussed the most parameters that might affect the behavior of the GFRP reinforced columns. This included replacing main longitudinal steel and stirrups with GFRP bars and sheets in two forms. Those forms were warped the longitudinal reinforcement of the column and bent the square column from the outside. Also, the reinforcement percentage was taken as a variable. 29. Tejas Joshi et al., 2016, the impact of different aggregate sizes and water-cement ratios on pervious concrete was investigated. The experiments are carried out to determine the void ratio, permeability, strength, and density of the material. It was discovered that when the strength increased, the density began to rise as well. 30. Yehia et al., 2017, porous concrete's characteristics were investigated to expand its structural engineering applications. Physical parameters including density, permeability, and porosity, as well as mechanical parameters like compressive strength, indirect tensile strength, and flexural strength, were investigated. Increased cement content increases compressive strength, indirect tensile strength, and flexural strength, according to the findings. Porous concrete has a lower density than conventional concrete by 21%, yet its permeability factor is 16 times that of normal concrete. Although increasing the cement content has no impact on the ultimate load or maximum deflection of polymer impregnated porous concrete slabs, the results demonstrate that this concrete can be utilized in structural engineering applications and that it is simple to cast special concrete like polymer concrete without the use of special tools. 31. Yehia et al., 2020, the research of fresh and hardened concrete characteristics was presented in this research. To get the best ratio, 18 samples were made with 3 different mixing ratios. Samples mostly consist of cement, water, and polyester, as fixed proportions, but the total coarse weight as a variable factor. In addition to taking into account the concrete density and void ratio, the collapse mechanism was observed and categorized. The researcher concluded from the experimental data that increasing the total coarse weight in the fine-free mixture increases the density of the samples while also increasing their flexural strength, compressive strength, and indirect tensile strength. 32, 33. 2. Experimental work program. Porous lightweight concrete was produced by utilizing two types of aggregate: lightweight expanded clay aggregate, LECA, with replacement ratio 0, 15, and 25%, and crushed stone aggregate, dolomite. Two different cement contents were utilized, 200 kg per cubic meter and 350 kg per cubic meter, and resin, unsaturated polyester in addition to peroxide as catalyze, with ratio 0 and 15%, from concrete volume were utilized to study its integrity with GFRP bars on the results. Compressive strength, indirect tensile strength, flexural strength, and dry density of different concrete mixtures were examined after they had hardened. Study of the structural behavior of polymer impregnated porous concrete slabs in bending. Table 1 demonstrates the different mixes studied in this research. Mix 1 contains no LECA, while mix 2 has less dolomite than a mix 1. In addition to the presence of LECA, mix 3 contains more LECA and less dolomite than a mix 2. Regarding mix 4, it is similar to mix 1, but has different cement content and more water content. Mix 5 is similar to mix 2, but with other cement content and water content. The same case can be seen in comparing mix 3 and mix 6. Concrete ingredients were tested according to ES 1109/2000 and 234 for aggregate and ES 4756-1/2000 and 935 for cement. Table 2 demonstrates the physical characteristics of the utilized crushed stone. Table 3 demonstrates the sieve analysis results for coarse aggregate. Table 4 demonstrates the physical characteristics of the utilized sand. Table 5 demonstrates the characteristics of utilized cement, Sameh 42.5 N. Table 6 demonstrates the physical characteristics of the LECA aggregate. Table 7 demonstrates the sieve analysis results for LECA aggregate, and Table 8 demonstrates the physical characteristics of the utilized unsaturated polyester. Also Table 9 demonstrates the characteristics of GFRP bars. It's worth to be mentioned that clean tap drinking water was utilized. An experimental work program consisting of two different phases was prepared. Phase 1 included testing of cubes, 10x10x10 cm in determining compressive strength at 7 and 28 days as demonstrated in Fig. 1. Testing of cylinders, 10x20 cm to determine indirect tensile strength at 28 days as demonstrated in Figure 2, and finally, testing prisms, 10x10x50 cm to determine flexural strength 28 days as demonstrated in Figure 3. Phase 2 included testing 6 slabs with dimension, 10x50x120 cm and reinforced with GFRP mesh with a diameter of 12 mm. Only 3 slabs were impregnated with 15% resin of slab volume and were tested under the impact of bending moment. The test setup of slabs can be seen in Fig. 4, with 2 hinged ends and 1 concentrated load in the middle. 3 results, analysis, and discussions. A digital testing machine with a capacity of 200 tons was utilized. The testing was carried out per BS 1239036. Cubes, cylinders, and prisms were tested for compressive strength, indirect tensile strength, and flexural strength after 7 and 28 days, respectively. The test results for all mixtures were summarized in Table 10, below. It was also discovered that steel fibers improved the mechanical characteristics of both traditional and lightweight concrete at various ages. The improvement in traditional concrete was more noticeable than in lightweight concrete. The reason for this can be attributed to the percentage of aggregate utilized in conventional concrete. Furthermore, the use of GFRP external sheet increased the enhancement magnitude. The hardened property test results for all mixes are demonstrated in the Table 10, below. Fig. 4 demonstrates the mix name and the corresponding compressive strength at 7 days and 28 days. The figure indicates that the compressive strength at 28 days is higher than at 7 and 28 days by 71%, 80%. Fig. 5 demonstrates the impact of cement content on compressive strength for all different mixes. The test results demonstrate that by increasing the cement content from 200 kg per cubic meter to 350 kg per cubic meter, the compressive strength at age 7 days increased by 300%. This can result from the comparison between mix 1 and 4. The impact of increasing the cement content on the compressive strength at age 7 and 28 days decreases as the percentage of LECA increases. Compressive strength at 28 days increased by 2 times, as seen from the comparison between mix 3 and 6. When mix 1, 2, and 3 are compared, the impact of LECA replacement is discussed. As can be seen in the figure, LECA replacement increases compressive strength by up to 2 times. The cement content raised the indirect tensile strength by 20%, as demonstrated from Fig. 6, from the comparison of mix 1, 2, and 3. LECA replacement increases indirect tensile strength by up to 27%. Fig. 7 demonstrates the flexural strength of different mixes, where the cement content can improve the results by 11% when increased according to the comparison between mix 2 and 5. The impact of increasing LECA is about 100% depending on the comparison between mix 1, 2, and 3. The density of different mixes is demonstrated in Fig. 8, where changing the percentages of LECA has no significant impact on the results. Fig. 9 reveals the impact of LECA and polyester on the compressive strength. Compressive strength decreased by 6% when polyester was added to the mix that contained LECA with 15% replacement. On the contrary, indirect tensile strength is improved by 30% when the polyester was added with LECA with 15% replacement, as demonstrated in Fig. 10. No clear impact to the results was noticed when adding polyester to LECA with 25% replacement. The flexural strength was slightly decreased by 4% when 15% polyester was added to LECA with 15% replacement, according to Fig. 11. Adding only the polyester to the mix by 15% increased the compressive strength by 300%, as demonstrated in Fig. 12. In comparison, it increased by only 66% in the presence of LECA. The impact of polyester was 66% improvement in the indirect tensile strength, but it was 355% in the presence of LECA, as illustrated in Fig. 13. Flexural strength of mix 1 increased by 3.5 times when polyester was added, but it increased by 36% in the presence of LECA and polyester, as demonstrated in Fig. 14. The load deflection curve based on test results of slabs is discussed in Fig. 15. It demonstrates brittle behavior for S1 and S6, meanwhile ductile behavior is observed for S4 and S5. S4 is more ductile than S1 because of the increased cement content. The presence of LECA decreased the ductility of specimens, which is clear from the comparison between S4, S5, and S6. Surprisingly, the opposite happened for S1, S2, and S3. It is obvious that S3 is more ductile than S2. The deflection of S1 was 33 mm. Meanwhile, it was 15 mm for S6. On the other hand, the deflection of S4 was 25 mm. From Fig. 16 and 17, it is concluded that slab S3 had less midspan deflection and ductility by 33.2% and 45%, respectively than S2. For slabs with 350 kg per cubic meter cement content utilizing 25% LECA replacement, there was an increase in midspan deflection, reduction in stiffness, and decrease in ultimate load by 65% than 15% LECA replacement. For slabs that contain 15% LECA replacement, 200 kg per cubic meter cement content and impregnated with 15% polyester cracking load, failure load, and ultimate midspan deflection increased by 64%, 141%, and 60% respectively than slab containing 350 kg per cubic meter cement content without polyester. Utilizing 25% LECA replacement and 350 kg per cubic meter cement content gave a similar slab behavior as utilizing 0% LECA replacement and 200 kg per cubic meter cement content. For conclusions. The compressive strength in 7 days is 71% to 80% of the compressive strength in 28 days, according to the experimental results. In 0% LECA replacement mixtures, increasing the cement content from 200 to 350 kg/m3 increases the compressive strength, indirect tensile strength, and bending strength by 300%, 120%, and 111.1%, respectively, while LECA replacement at 15% and 25% decreases the density by 3.1% and 5.6%, respectively. Compressive strength increased by 100% and 220%, indirect tensile strength increased by 24% and 27%, and flexural strength increased by 71% and 100% for mixtures containing 200 kg per cubic meter of cement and 0% LECA substitution, for mixtures containing 200 kg per cubic meter of cement and 0% LECA substitution, for mixtures containing 200 kg per cubic meter of cement and 0% LECA substitution, for mixtures containing 200 kg per cubic meter of cement and. It has also been discovered that utilizing 25% LECA substitute and 350 kg per cubic meter cement content produces the same slab behavior as utilizing 0% LECA substitute and 200 kg per cubic meter cement content. As a side approach, utilizing slurry cover as a shutter for impregnated polyester would be highly cost-effective. However, for testing purposes, it leads to a lot of measurement inaccuracies.